How are y'all? Nice to see you all again. Hopefully you had a nice break. Unfortunately, it was good. I didn't do any work. I answered emails, but but I mean, it's the last break till Thanksgiving, so we're in it for the long haul. Reminder, we have our first exam Tuesday the 17th, which is 3 class periods from today. So we've got, we're going to finish 2.5 today and start 2.6, and then finish 2.7, or 2.6, and then start 2.7 our next class meeting. I'll probably have to finish 2.7 and review before the exam. So that's kind of how it's looking right now anyways. Does anyone have any questions over the homework?
Yeah. Present the guess the answer because it's pretty simple, but I was confused about what they were asking. I mean, number 6 and 4.4.
Is it this one?
Yeah.
Let me start a new document here.
I don't know what to do.
I'm trying to read it slow.
This is my chemistry or calculus
My name, like my
I feel like exactly how I would like to
Okay, so question in 2.4's homework asks, suppose f of x approaches negative 200 and g of x approaches 0, with g of x smaller than 0 as x approaches 5. Determine the limit as x approaches 5, f of x over g of x. So they're basically just having us put this information in as x approaches 5. F of x approaches negative 200. I guess we don't need the limit there anymore. But and g of x approaches 0. So we have this thing on the bottom approaching 0. And then they say that g of x is smaller than 0. So that means g of x is approaching 0 through what kind of values? Small negative values. So this is approaching small negative numbers. All right, yeah. So then.
So I was confused about the sign because it was either switching between infinity and negative infinity.
Right.
The end result. I wasn't quite sure how I was getting the variation between negative and positive.
Okay. All right. Yeah. So there you go. Denominator or the numerator is fixed. The denominator is getting smaller and smaller. That will always be an infinity for us. And then we look at the sign. It's a negative over a negative, which is positive. So that's approaching positive infinity. And what does that tell us about this function f of x over g of x? What do we know?
Asymptote 5.
Yeah. What kind of asymptote? Vertical, right? This is common notation for therefore. Therefore, we'll write f of x over g of x has a vertical asymptote at x equals 5. Okay. If we wanted to know what was happening, we would need to get a little bit more involved with the limit procedure here. So if we have this, here's our vertical asymptote at 5. If we wanted to know whether the function was approaching it this way, or this way, or this way, or this way, then we have to look at our one-sided limits from the right and from the left. So since we didn't do that, it's still unknown to us. But that's the nature of what we've determined. Any questions on that? Any other homework questions? Yeah,
We would get a 6 on 2.5.
on 2.5?
Yeah.
Okay, so let me make sure I label that 2.4, number 6, just in case people miss that. Number 6, okay. So the 2.5, I'm sorry,
Number 6.
number 6. Thank you. All right, so determine the limit x approaches infinity sine 17x over 20x. So what is the issue here? So x approaching infinity, technically not the issue, because we can approach infinity on anything we want to look at, really. So if you think about that, computing that limit, what's causing the problem? The sine of 17x, and how come?
Because the +1, -1 y-axis limits.
Is what? Sorry.
The +1, -1 y-axis limits on sine.
Well, you mean the fact that it's bound between 1 and negative
Right.
1? Yeah. So if we looked at that, the nature of that graph. It just keeps doing this forever, right? So as we go out towards infinity, does the sine of 17x ever approach something that we can determine? No. I don't know that we made a particular note of this in our class notes, but for sine and cosine, let's say positive and negative infinity to sort of shorten that. But if you're asked to compute the limit at infinity on sine or cosine, what would that limit be?
It wouldn't exist.
No.
Okay, it doesn't exist. What do y'all think? In other words, as we look at the end behavior of sine and cosine, does it flatten out or approach infinity? No, it's always in between 1 and negative 1. So that's the issue with trying to compute this problem. The numerator is approaching something that doesn't exist. What's the denominator approaching? Yeah, an arbitrarily large number. So normally we would say, well, if the numerator is approaching something that's finite and the denominator is getting larger and larger, what does that mean? Yeah, if we have some finite number over something that's getting larger and larger, what does this approach? 0. But that's not the case here because it's something that doesn't exist over something that's getting larger and larger. So how do we make sense out of that? Yeah, so does it not exist? I mean, intuitively we would think, well, something that doesn't exist over something that's getting larger and larger, we can't make any sense out of that. So perhaps we would think that it doesn't exist, but it's not necessarily that intuitive, I think. So we did look at a particular method to handle these kinds of things. Something we talked about in 2.4, or 2.3 rather. It's something you might eat. The squeeze theorem, yeah, the sandwich theorem. So let's look at that and see if it actually helps or enables us to determine what's happening here. So we have the sine of 17x. So we know that the sine of 17x is in between what and what? Okay. And the sine of arguments are in between 1 and -1. Okay. So we want that to look, we want to establish some inequality so that we have this mirroring our function that we're computing the limit on. So we then need to divide by 20x. So if I want this to look like my function, it has to have this 20x down here. But I've already established this inequality, so I have to have the 20x here and the 20x here as well. All right. So then, lengthy notation here, but we're going to apply the limit as x approaches infinity to all three sides, or all three parts. Hello? Okay. So then maybe you can see if that's going to be helpful or not. So do we have something definite on our ends? The limit as x approaches infinity for -1 over 20x or +1 over 20x. Okay. Which one?
0.
Okay, 0, yeah. And so I'll just star these two here on the end and reference back up here. So does that help us with our limit? Yeah, because both of these are 0. We know that this limit has to be 0. Okay, so therefore, that limit is 0. So we can make sense of that. Even though we had a limit that didn't exist over a limit that was getting larger and larger, something that doesn't exist over a large limit, and this case equals to 0. It's not always the case, but in this particular instance, it happened to be so. And that's what we'll see later on in chapter 4. Certain limits can take on any value, and we develop a technique so that we can actually determine what that value is. So let's also look at the graph. Maybe one of those funky graphs that's hard to tell, but at least we can. Okay, so before you guys spoiled it already. This was the graph for just sine, by the way, not the function. When we look at the limit as x approaches infinity on any function, what are we determining? End behavior. What happens at the end? So what does this function do at its very end? We said that that function at its very end approaches 0. So the function way out towards the end is flattening out towards 0. And so we can sort of see that if we zoom in. We see towards the origin, the oscillations are pretty large, but then the oscillations start to smooth out. It's not that we're saying that those oscillations, even for like super large values of x, it's ever flat, right? It won't let me do that. Let's try this. But as we get further and further and further out, we would expect those oscillations to be smaller and smaller, eventually flattening out. I'm just kind of curious now how far this will go. So that's we're still at 10 to the 9th here. All right, let's go 10 to the 10th. I mean, we might not be able to zoom in far enough, but you get the idea. So it looks pretty flat. Maybe you can start to see a little variation there, because I don't know. I guess it depends on how good your eyes are and how good the projector is. But there is a slight dip here. Anyhow, that's the graph. That's what we've done. So I'll just capture this portion. Based off that limit, the function approaches 0. I mean, you know, in this instance, we would say, well, there's a horizontal asymptote at y equals to 0, but we see that function is actually crossing a horizontal asymptote infinitely many times. But eventually, if we could take it out to infinity, we would see that it doesn't cross. At some point, it's not going to cross. We just can't go out that far. I mean, we can, because we just did, but that's the idea. Do y'all have any questions about that? All right. Are there any other homework questions? So we left off in 2.5. What were we doing in 2.5? What was the main idea in 2.5? Limits at infinity. Limits at infinity as x approaches positive or negative infinity. Again, those limits determine our function's what? And behavior. All right, and then we looked at all three cases that we probably saw in like an algebra or pre-calc class, where we said if the degree of the numerator is less than, or if it's equal to, if it's larger than, what kind of scenario do we have in terms of a horizontal asymptote? So we looked at all of those in the context of a limit, and then this last example we looked at was when the degree of the numerator is 1 larger than the denominator, the degree of the denominator. We had a slant or oblique asymptote, which was a linear thing that wasn't a horizontal line. But we had to look at the function in a slightly different way, because if we compute the limit at infinity on the function as it was given, the 2x squared plus 6x minus 2 over the x plus 1, then our work as far as the limit goes shows us that we didn't do it, would show us that it just approaches infinity, which again, our interpretation on that is there's no horizontal asymptote, because the limit didn't approach a finite number. We said let's look at it differently, where we actually divide these two things. So we have our quotient minus or plus the remainder over the divisor. And then we said, well, if we looked at the limit at infinity on that instead, the 6 over x plus 1 would approach 0. So for large values of x, the original function is going to look like 2x plus 4. So it behaves like, this function behaves like 2x plus 4. We should say this is for large x. So that was the example we ended on. Does anyone have any questions on that? It's still the same procedure that we apply to for limits at infinity on rational functions. So let's look at that as well. Oh, wow. I should pay attention to what I'm doing. Okay, so there's our function. It doesn't have a horizontal asymptote, but as our work showed, as we get further and further out, that function is going to start to look like 2x plus 4, which is a line. So that function starts to resemble a line as we get further and further out. So we see that cutting through the origin right there. If we plot the line 2x plus 4, we see that it's the same thing. I don't know if you can see that changing colors or not, but of course if we get in close, then the function doesn't look like 2x plus 4, just for large values of x. So all of that stuff that you learned in regards to these types of asymptotes are still applicable in the context of limits. It's just that we're looking at it through a different lens is all. Everybody cool with that? Gonna move on then. So this is sort of an aside, but it does prepare us for certain types of limits, and we'll see an example of that next. So what if you were asked to compute the square root of x squared? We just get x, the square root of x squared. Does that equal to x? Plus or minus x, maybe? So I mean, it seems reasonable, but let's just try to check that. We'll just pick a number. I'll just say 4. What's the square root of 4 squared?
4.
It's 4. So it certainly seems to work out, right? Here's my x. I got x back. But it gets a little weird when we look at a negative number. What's the square root of negative 4 squared? It's also 4. Well, if this is our x that we're plugging in, this is not x, this is negative x, right? So this certainly doesn't seem to work.
The absolute value.
Yeah, absolute value, which was kind of indicated with the plus or minus x. So I'll write it up here. The square root of x squared is equal to the absolute value of x. So then that would work, right? If this were our input x for our square root of x squared, and we say the output is the absolute value of 4, which is 4. So our input matches our output. Same thing here. We would have to say that this is the absolute value of our input. So now that works, right? So it might be something that you were shown or taught, but I don't know that it's that common. I think usually people will just say, well, they're inverses, so they undo each other, so you just get x. But the fact is it depends on where you're at, right? That's what the absolute value function tells us. It says it depends on where you're at. Yeah, you always get a positive number, but depending on where you're at, you have to look at it in a slightly different way. Now, extending that pattern, what's the square root of x to the 4th? Okay, what do y'all think? The absolute value of x squared? Okay. I would say that's correct. However, do we need the absolute value there? No. How come we don't? Yeah, how come we don't need the absolute value?
Any squared, it'll make it positive.
Because anything squared is already positive, right? So the absolute value of x squared is just x squared. What about the square root of x to the 6th?
X
X what?
to the 4th.
No, not x to the 4th.
I mean, to the 3rd.
To the 3rd? Okay. X to the 3rd, what do y'all think?
You need an absolute value,
Yeah, why do we need the absolute value there?
given odd versus an even exponent.
Because something to the 3rd power could be positive or negative. So x cubed could be positive or negative. Thus we need absolute value.
So does that stay consistent where the exponent inside of the root, in this case the square root,
Mhm.
or whatever it is, cubed or whatever it may be,
Yeah.
is it generally an absolute value if you have an even and an odd, like an even and an odd exponent?
Right.
Versus an even and an even exponent, they stay the same.
Yeah,
Generally, there's no absolute value needed,
that's correct.
right?
Yeah, and another way to think about that is put the absolute value there. If you have x to an even power as the result of the root,
Right.
then you don't need an absolute value because even powers always give us a positive number. But when we take the root of something, well, I should be more specific, when we take the even root of something that gives us x or something to an odd power, that's when you need the absolute value because odd powers could be positive or negative. Oops, I can't count. Okay, so a couple more. What's the square root of x to the 8th?
X to the 4th.
X to the 4th. X to the 4th, always positive, don't need absolute value. What's the square root of x to the 10th?
X to the absolute value of 5.
So that's the absolute value of x to the 5th. So I guess we could say, let's generalize this. The even root of x to a power is equal to the absolute value of x. And we'll just abbreviate this. The absolute value of x to the power of n if capital N is odd. If we're dealing with cube roots, we don't have to worry about that, right? Because cube roots, or odd roots rather, can be positive and negative. It's only the even roots that have to be positive. Yeah. Well, just for simplicity, we should say P is a positive, well, not positive, we should just say P is an integer. So that's sort of an aside. The next example we'll see like why we have to think about it that way or why we care. Does anyone have any questions about any of that? Okay. So in practice, if we were asked to state the end behavior of this function, first of all, what does it mean when you're asked to state the end behavior? At the end, right? So the end behavior is two things. The limit at infinity and the limit at negative infinity. We did make mention of when it was sort of a shortcut way with a certain type of function where the limit at infinity and negative infinity would be the same. So what type of function would the limit at infinity and negative infinity be the same?
Say that again?
When would it be sufficient to compute the limit at infinity or negative infinity, not both? What kind of function would we have to be dealing with?
Piecewise function.
The what?
Piecewise function.
Not necessarily a piecewise function.
I suppose that's one sided limit.
So the exponents always, the same root negative and positive.
Yeah, so if like you think of stuff like 2x cubed or something like that.
Yeah, or not necessarily cube, like the 6 power.
Yeah, it's the even powers. Remember the even powers? Yeah, they have end behavior that look like that. Okay. What else?
Anything with a horizontal asymptote?
Anything with a horizontal asymptote, which is typically, not typically, but for us, we saw that with what kind of function, I should say.
Polynomial.
Polynomial would be these for even degrees.
Rational function.
Yeah, rational functions, right? When we have a polynomial divided by another polynomial, if you compute the limit at infinity and the limit at negative infinity, it'll tell you the same thing. So we did make note of that. When you're computing end behavior or determining end behavior of rational functions, it's sufficient to look at just one of those, but only for rational functions. If that's confusing, then just compute both limits, because end behavior is both limits. It's just that special case where we're dealing with a rational function that it's sufficient to look at just one of those. So we need to compute both of these limits because this isn't a rational function. It has that square root in the bottom.
Choose the long way we talked about last week.
Yeah.
Dividing the top by x to the third power, and the
Uh-huh.
bottom by x to the sixth power.
Right.
Simplifying that.
Yep. So remember, we had a short way and a long way to do these things. The long way, it said to compute a limit at infinity with a quotient in powers of x, you look for the highest power of x in the denominator, and then you divide everything by that power. I'm not going to actually compute it the long way, but I think it's important to look at it so we can just kind of work through what's happening.
I was gonna say, can't we just simplify the denominator so the square root is everything?
In what way would you simplify?
Could we put the square root on each individual value? So like the square root of 25x to the 6 plus the square root of x to the 4th plus the square root of 2.
Yeah, so you have to remember that when you take the square root of, sums or differences, that it doesn't equal to the differences of the roots or the sums of the roots.
You have to take that whole thing to the power of 1/2, right?
Yeah.
The parentheses and that whole bottom would go to the power of 1/2 as a whole.
It is valid, however, when we have a product, and we're assuming we're dealing with real numbers. And of course, we know that a product is also a quotient, so it's valid for products and quotients, not addition and subtraction. So I think in general, we can't do that, but in the context of what we're actually doing, we can do that. And we'll sort of see that in a minute. Let me just indicate that this is the longer way. Let's see if this works. just trying to cheat.
Man, I wish I had copied and pasted on this paper.
Work smarter, not harder.
All right, so if the longer way says we've got to take the highest power of x in the denominator and then divide everything through, I guess the reason to pause is to say, well, the highest power of x in the denominator looks like it's x to the sixth, right? But in reality, we're taking the square root of that. So it's a matter of which function you're dealing with. If I come in here and divide everything under this root by x to the sixth, that's totally fine, but I need to divide everything up top. Not by x to the sixth, but x to the third, right? Because I'm taking the square root of x to the sixth. But what did we just say was the square root of x to the sixth?
X to the third.
The absolute value.
Absolute value of x to the third, right? Okay. So
So
just-
why is it, one more time, why you run that bottom denominator different than you do in the numerator?
because the denominator has a root attached to it,
Okay.
the numerator doesn't.
Okay.
So if we couldn't divide everything in the denominator, if we wanted it under the root, we wouldn't divide it by x cubed. If we wanted under the root, we'd have to square it to put it back in the root. So it's x to the sixth. I mean, this is, we'll modify this a little bit, but this is essentially what we're doing. Is everybody okay with that? Either way, the long or the short way, you have to think of it that way. Otherwise, you're going to get incorrect results. And then so we would say, do we need the absolute value here on this piece to compute the limit at infinity?
No.
No. Why don't we need the absolute value on x cubed here?
Because we're dealing with positive values. Going
Because-
towards positive infinity.
Right, because x is approaching a large positive number, right? The only reason we had to have the absolute value there is because, in general, when we're dealing with this thing, we don't know where x is. X could be positive or it could be negative, so we're just going to ensure that it's always positive regardless of where x is. However, when we compute this limit, we know exactly where x is. It's a large positive number, so we don't need the absolute value there. Okay. So I'm going to erase this limit because this is the way we're going to think about it. And depending on where x is going to determine what we're dividing through by in the top. So we compute that the long way. If you want to just verify that what we're doing is actually the result we get when we look at it with the shorter way, then feel free to do so. And, you know, we have to be careful, but we're computing, we'll do both of these the short way. So the limit as x approaches infinity. I'm just going to rewrite the function and then talk about what's happening. Oh, jeez. I still haven't figured out what's the time limit before it groups something together. I'm not quite sure what that is.
Just do
So remember what we said previous to when we were computing limits at infinity on rational functions. We said I can look at the dominating term in the numerator and the dominating term in the denominator. So as far as the limit goes, this is equivalent, as long as we're computing limit at infinity, this is equivalent to looking at the 10x cubed over the square root of 25x to the 6th. Is everybody okay with that? It's kind of in line with what we did last week.
And at this point, can we simplify the square root in the denominator?
Yeah.
It's just one value.
Right, so it's just we have that single value now. And again, it's not that we're taking the square root of all of these things individually. It's just we're saying that as x approaches infinity, the contribution of this x to the 4th and this 2 are smaller and smaller. So we don't have to pay attention to those. But only out at infinity. So let me just make this even more generic here. And I'll just note that this is, they're asymptotic to each other as x approaches a positive or negative infinity. Okay. And then so we take 10x cubed over the root of 25x to the 6th. And we simplify that. Again, we're not specific on where x is, so we have to say, well, the top is still 10x cubed. What does the bottom simplify to if we don't know where x is?
5, the absolute value of x.
Right. So I mean, that's just an algebraic simplification, but a large part of that is based off the fact that we're about to compute the limit at infinity. So that's why we were able just to look at the leading term over the leading term, if you will. If that was just an algebra problem and it said simplify this, you can't do that. That doesn't simplify to what we have unless we're computing limits at infinity. Is everyone clear on that? I've seen sort of a disconnect between when we can do that and when you can't do that on exams. So just make sure that you're clear when we can look at leading term over leading term versus when we can't. Very important.
And when can't you?
So like if we were asked to compute the limit on this thing as x approaches some finite number,
Then we can just solve it.
Then you just
yeah, then you just plug in, assuming that the function's defined at 10, or we're able to do that. Okay. So the limit at infinity, positive or negative, simplifies to this right here. Again, we're just looking at leading term over leading term. Is everyone okay with where we're at? So then when we compute the limit as x approaches infinity on 10x cubed over 5 times the absolute value of x cubed. Again, we know that x is positive. Right. So we're just computing the limit as x approaches infinity on 10x cubed over 5x cubed. We don't need the absolute value when we know that it's positive.
We simplify that out to just be 2.
Yeah, so simplify this, the x cubes divide out, 10 over 5 is 2. So that weird function has a horizontal asymptote at y equals to 2, as long as we're going in the positive direction. What happens if we have to compute the limit as x approaches negative infinity on that function? But this time x is a large negative number. What's the absolute value of x cubed when x is negative? Negative x cubed. Negative x cubed. Yeah. So just, it might be helpful at this point to recall what is the definition of the absolute value of something. Well, it's the thing itself if the thing itself is positive or 0. It's the opposite of that thing if that thing is less than 0. Do y'all remember that? So if I put x cubed in here, that's the same thing. It's the thing itself if it's positive, but it's the negative thing if it's negative. So the limit as x approaches negative infinity, if we're rethinking the denominator, is just 5 times negative x cubed. So this one's, we'll just put an asterisk here, and asterisk here. Right, which is just negative 2. Again, the x cubes divide out. We have 10 over negative 5. Which is negative 2. If you forgot, if you don't apply that reasoning to these types of functions, then you're only going to come out with one horizontal asymptote, when in fact it has 2 different horizontal asymptotes. Yeah?
I thought the absolute value had to be positive, so I'm missing the logic jump as to why it would be negative 2.
Okay, so the absolute value outputs something that's always positive, depending on the input,
Okay.
right? So the reason we have to make everything negative here is because we're plugging in negative numbers. So if I plug in a negative 8 or a negative 2 and cube that, I get a negative 8. But then I have to multiply it by that negative 1, which gives me a positive 8. So if all of those negative values, if that wasn't there, they would still be negative.
Can be the negative product versus 5 on that?
Well, technically the negative is coming from the absolute value of x cubed when that thing's negative. So the absolute value of x cubed is negative x cubed if that input is negative, which it is because it's a large negative number. So that's the absolute value of x cubed turning into the negative x cubed.
Okay, yeah, no, I was just thinking because I thought that cubes, like if you were dealing with negative numbers, they're negative, positive, negative, right?
Say that the cube of a negative number?
Yeah, because you're multiplying it by itself by negative, so the first round you end up with a positive number, right? You end up with negative, negative, positive.
No, because you always have 3 negatives multiplied by each other. So the negative times the negative is the positive and then the negative again.
Yeah, I think we're saying the same thing.
Okay, but it doesn't jump in value from positive to negative. It's always
Well, that's
negative.
just incrementally doing it, like each exponential value.
Okay, okay. So think about it that way if you want. But yeah, the cube root of a negative number cubed is always negative.
Science alone.
Yeah. So any other questions or comments on that? I know it's kind of weird at first because we're not typically accustomed to thinking of it that way. Again, it's crucial that we think of it that way. Otherwise, we're just getting the positive 2 as the limit, which is not the case. Where did my thing go? I don't really need all these terms
Times another negative is a negative.
at infinity, but we'll just go ahead and put it
Because you're
in.
negative, so that always on the left side.
All right, so there's the function. It's kind of weird, but again, once we zoom out, we can see that the thing starts to flatten out at both positive and negative 2. See that here? Again, we have a dip below the horizontal asymptote, but notice the behavior as we get further and further out. It's starting to approach that line, y equals negative 2. Do you have any questions about that? Okay, there's a similar one in your homework here. Granted, we didn't have that additional term on ours outside the root, but the same reasoning is going to apply here. If I look at the leading term in the numerator, it's 4x cubed. And the denominator, I have this 4x cubed here, but what do I get from the square root of 64x to the 6th? Yeah, so that would be the leading term in that root is 8x to the 3rd, right? But really we need to think about it depending on where x is, it's 8 times the absolute value of x cubed, right? So you really have essentially like 2 leading terms in the bottom that you have to combine at some point, but you wouldn't combine them until you looked at the absolute value. If x is positive, then that's just 8x cubed. If x is negative, then it's negative 8x cubed. And then you could combine those 2 terms in the bottom. It's just slightly different, but the reasoning that we just worked through with the absolute value is still has to be applied here in number 13. Okay. So if you have any issues with that, just let me know. We can talk about it in class or whatever is appropriate.
So do you only really need to consider the negative value like we did with the negative 2 if the domain of the x is looking at a negative infinity?
Yeah, right. So because you're way out here
Right.
with negative numbers, so that input's always negative as you
So more
go
than
that way.
anything, you're those times, even if you end up with like x cubed or x to the 3rd power, even though the limit is only looking between the 1st and 4th quadrant, the negative is irrelevant because
Right.
it's not there. to
Exactly.
begin with.
Yep.
Okay.
Okay. What's the end behavior of e to the x? Why is this scary? Do y'all remember the graph of that? What?
That's descriptive.
The what?
The little, it goes up to infinity on 0 and then sideways that direction.
Yeah.
Yeah?
Yeah.
Okay.
Right.
I wasn't really sure if that was that.
So let's think about it. Some of you might remember the graph, but let's say we forgot the graph. What's the end behavior of e to the x? Well, end behavior means compute the limit at infinity and negative infinity. So maybe we can think about this in a calculus perspective. So the limit as x approaches infinity on e to the x, I mean, isn't that kind of like e to the infinity? What is e to a super large number?
Positive number.
A super large positive number, right?
The limit lies on
But is
zero.
infinity an even degree or an odd degree?
Say that again.
So is infinity even or odd?
Neither.
Neither.
Infinity is an idea. It's not a thing. It's not a number in that sense. It's a concept.
That didn't sound like psychology.
Well, it kind of is philosophical if you really think about it. Like you could never get out towards infinity, but you know, with a little bit of a mathematical tweak, we can say, well, if we could get out to infinity, here's what it would be doing.
There's multiple infinities anyway.
So what? Do what?
There's multiple types of infinities anyway.
Right. Yeah.
If you could do an infinity of primes, right?
Mhm.
That's larger than a regular infinity.
Yeah.
In a sense, it's, yeah.
Yeah, so there's infinity in the sense of approaching finite numbers. I can get infinitely close. There's infinity in terms of infinity getting larger and larger. And then there's countable infinities. And then there's uncountable infinities. So there's, the guy that did this, like, actually was in a mental institution for a while, so don't think about it too hard.
Yeah.
Don't think about it too hard.
I mean, I don't blame him.
His name was Georg Cantor, if you want to look him up.
First of all, what kind of name is that?
There's a lot of components of chemistry.
kinda
that
went
are the
crazy
same
though.
thing with infinities per se.
Yeah.
Never reaching zero. You know, when you touch something,
Right.
you know, you're never truly touching something.
Yeah.
Technically.
In the sense of a limit, that's
right,
true.
Right.
Yeah.
It's almost like that. You know, your hand is that line and the wall is zero.
Yeah.
You may feel like you're touching it, but in an aspect of physics, you're never truly touching an object.
Yeah, right.
It's never.
Right.
There's never full contact.
Yeah.
Wait, who was in the mental hospital? Like the guy who figured out what infinity was?
No, he was classifying the different types of infinity. There's a countable infinity, and then there's an infinity that's not countable. Yeah. So that's what we're looking at. As x gets large in the positive sense, the function gets large in the positive sense. What about the limit as x approaches negative infinity on e to the x? Yeah, 0. So let's just plug that in. E to the negative large number. What do we do with negative exponents to make them positive?
Flip, like 1 over e out.
Yeah, we flip it over, right? 1 over e to the positive infinity. And we already know that e to the positive infinity just keeps getting larger and larger. So what's a fixed finite number over a number that gets larger and larger and larger?
Smaller and smaller.
It gets smaller and smaller and smaller. So out here, the function's doing that, getting closer and closer to 0. Did I remember the exponential function now? Looks like that, with this point at 1. Okay. I think it's super helpful to remember that. You should remember that. If you didn't remember that, then we've only got, with these two limits, you only have I guess a small piece of the graph, right? Where's the arrow at over here? Where's the arrow at over here? What's happening in between? It's helpful to know. Okay, so then we can look at that in combination of other functions like 7e to the x minus 15 over 3e to the x. What's the limit at infinity on that function? Oh yeah, my bad. Now it's 2 eyes that are closed. So the idea is still prevalent here. If I'm computing the limit at a super large number, does the minus 15 here really account for anything? No. So in the sense of a limit at infinity, I can just look at the leading term or the dominating term on top and dominating term on the bottom.
7/3.
And what does that give us?
Even though E is a value and not a number, or a number and not a letter like a value or something.
A variable, yeah.
Variable, yeah. Could we just technically cross it?
Right. Yeah, because e to the x divided by e to the x is always 1. So it's just 7/3, yep. Not bad, right? But you gotta, some people will think, well, the numerator's approaching infinity and the denominator's approaching infinity. While that may seem like the case when we first look at it, the fact of the matter is that they're approaching, if we looked at them individually, they're both approaching infinity at the same rate, or at a very comparable rate. The comparable rate here is 7/3. So it's just not infinity over infinity. I mean, it is when you directly substitute. We've yet to talk about infinity over infinity or 0 over 0 in the sense of a limit. Excuse me. But infinity over infinity or 0 over 0 can take on any value. So I don't know, we don't really talk about growth rates. The rate of growth of these two functions on top and bottom are comparable because they're approaching a finite number. Sometimes you can have functions on top that grow much more rapidly than the functions on the bottom, or vice versa. I don't know if this is, like if we had 7e to the x over 2x squared, that's not a rational function anymore. But when we look at, okay, well, this is the dominating term over the dominating term, well, what's happening? It's still they're still both approaching infinity, just like this one was. But the exponential grows much more rapidly than the power of x. So the numerator is going to reach infinity a lot more quickly than the denominator reaches infinity. So this thing actually, the limit at infinity on something like this is actually infinite, whereas if we had 2x squared over 7e to the x, the limit here is actually 0. So there are some nuances here as far as like, oh, well, I'm computing a limit at infinity, I just plug infinity in. I mean, while that works in some instances, it's not beneficial to look at it that way in most instances. So sorry if that was confusing. I just, these things need to be said because we get to the point where we see like 1 or 2 examples and think it works that way every single time. And the fact of the matter is that that's not usually the case. There's always an exception. If there's not an exception, then that's when you see the theorems. Okay. What's the end behavior for the natural log of x? By the way, does anybody recognize that graph that's on the back board right there?
Yeah.
It looks like a graph.
Very interesting observation.
It probably has something to do with calculus.
So yes, it's been there for more twice.
Oh, that's that graph.
Yeah, that's that graph.
Oh.
I mean, so in a sense, it's helpful to remember the graphs because when you're asked to find the end behavior, then you say, I don't know what the graph looks like. What's the limit at infinity? And what's the limit at negative infinity?
It exists at negative infinity. Only exists at positive infinity.
So does this one that you're talking about,
Yeah.
does this limit exist, the limit as x approaches infinity, the natural log of x?
Yeah, it's just infinity, isn't it?
And
Just infinity.
It doesn't exist because the graph shows that as it approaches, as x approaches 0, it's approaching infinity.
Right.
So therefore, it cannot approach negative infinity over x because it can't go that way.
Correct. Yep. So that's another thing that we have to pay attention to. we've, up until this point, we've seen n behaviors at infinity and negative infinity. But it depends on the function, right? Like the domain for the natural log of x doesn't include large negative numbers, right? So there's nothing to approach in that sense. There's no function for large negative numbers. So you also need to be aware of the domain for these functions. The domain of this function is from 0 to infinity. So it makes sense to compute the limit as x approaches infinity. It doesn't make sense to compute the limit as x approaches negative infinity. On this end, not negative infinity, but what makes more sense as we approach what?
0.
0. As we approach 0, because the natural log isn't defined for negative numbers. So really we should be computing the limit as x approaches 0 from what direction?
The right.
From the right. Right, because our domain here is that. It only makes sense to compute the limit as x approaches 0 from the right. So the problem with the natural log or logarithms in general is that they grow very, very slowly. So if we look at it from this perspective, we can see, yeah, there's definite growth to that. It's not leveling out, right? But the slowness of growth becomes really apparent when we start to zoom out. If we zoom out far enough, it just looks like it's flat, right? So for an input of 2500, the logarithm is outputting 7.4. So in looking at the graph in that sense, we might think, well, does it actually approach infinity? Did these values get larger in this direction? So how do we know that?
That it's growing?
Yeah, that this function just continues to grow as x gets larger and larger.
I mean, I guess in all technicality, don't. It's a very, very well-educated guess based on behavior. But in order to just technically make that assumption, you'd also have to have an n value. Infinity has no n value. It's a trend, more than anything.
Yeah.
Very well-educated determination based off of trend.
So you can look at values, like
Right,
it's
but
7.8 at 2500,
Right.
it's then 8.1 at 3000.
But there's nothing to technically calculate to give you. At that point, it's a theory, not
Okay.
not a law or an absolute in any way. It's just a very well-developed theory.
I would say on the surface it appears that way, but that's not the case.
No?
Could you say because it's the inverse of the exponential function and we know that the exponential function grows and grows and grows, and considering you're just flipping it on its side, then that can help prove that it does keep getting larger and larger?
Yeah, exactly. So remember the connection to functions and their inverses. If I looked at this function, whose domain is what? Yeah, I can plug in all real numbers into the exponential. Versus its inverse, which is the natural log of x. the domain on this function corresponds to what on the inverse?
Range.
The range. Yeah. These are the same. So how does that tell us that the limit at infinity is infinity? Well, that's the set of outputs, right?
Yeah.
That's what, no matter what we plug in, the function eventually outputs every number in the positive sense. So that's how we know this limit is actually infinity.
Are we going to have to memorize this?
I would know it, yeah, because I mean technically this was sort of a precursor to what we're doing here, yeah. I mean, I don't want to ever say, no, you should know what the graph of e to the x looks like, because all you're doing is computing limits. You know, that would not be a good teacherly thing to say. You should know this stuff. I'll just try to narrow it down when exam time rolls around. Okay, and then the limit as x approaches 0 from the right is negative infinity because of the vertical asymptote. And again, we can reason through that by looking at the range of e to the x. As we saw in this graph, the range of e to the x was from 0 to infinity. That's the domain of the inverse function. So range and domain just switch when we talk about inverse functions. Okay. All right, so that's, you should know the end behaviors of these functions for sure. All right, so that was sort of an aside thing. Does anybody have any questions at this point? Yeah, so it's sort of weird. Up to this point, you sort of looked at all of these things in bits and pieces, right? They were always, in effect, isolated from each other, but when you get into calculus, it's like it's all there. So that's really when you have to start recalling, you know, past stuff, because it's just all thrown into the pot. All right, let's take a break and then we'll. I think we're actually finished with 2.5, so we'll start 2.6.
The first time one.
Oh, ready?
And so that's why she just let it slide. Because I was 1% away. Yeah, and so I technically had to pass the test in order to pass the class, but I was 1 point away, and then I retook it and got like 10 points below.
It's not very loud.
You have to plug it into the thing.
I'll figure that out. All right, let's start 2.6. So in 2.6, we're going to look at basically 3 main concepts. Continuity at a point, continuity along an interval, and then we'll look at an implication of continuity. So the informal definition of continuity that we all dealt with, I think, up to this point was if you can draw the graph without picking up your pen, then the function's continuous on that interval. So, you know, a couple of examples where that definition is actually makes sense. So this is a continuous function. This function on the right, clearly not continuous. So it was sufficient for the things we encountered up to this point. But, you know, if you remember a graph that we looked at that was similar to this, we had those like infinite oscillations towards the origin. The idea of picking up my pen doesn't really make sense because we can't tell what's happening at the origin, which means we need a more definitive definition of what continuity actually is. Okay. So particularly at the origin, we want to know, is that continuous? Is there a break or a gap there? There's no way to determine that just by our informal definition of continuity. So then we can say, well, let's more precisely define continuity. So here's our definition of continuity at a point. We say a function is continuous at an x value of a if the limit as x approaches a on that function is equal to f evaluated at a. So in other words, does the limit equal the function value at that location? So this is the definition of continuity, and notice it's defined in sense of a limit. The limit or the statement in this definition is actually broken down into three components, because it's actually three different things we have to ensure in order for the limit to equal the function. So our continuity checklist that we have here, this is kind of what we're going to use to determine continuity. If any question asked, is this function continuous here, then we've got to make sure that we're justifying all three of these. Okay, so our continuity checklist is used to justify continuity. And so in order for the limit at as x approaches a to equal the function at a, then first of all, f of a has to be defined. The function has to exist at that value. And they're sort of nested. If 1's not true, then 2 and 3 can't be true. If 1 is true, but 2 is not true, then there's no way 3 can be true. So it's sort of spelled out in this hierarchy of how things are put together. So the function has to be defined. The limit has to exist, but it's not enough for the limit to exist and the function to be defined. The definition actually says that the limit has to exist as the function value. So that's item number 3. So let's use the definition of continuity, and we're going to look at this weird piecewise function here. H of x is x sine of 1 over x when x is not 0. The function is 0 when x is 0. So we want to know, is that function continuous at x equals to 0? So we have to run through the checklist. Number 1, oops, not the limit yet. Number 1 simply asks, is f of a defined? And here's our a. When x is fixed as a particular value, then that's our a. So is f of a defined? In other words, can we compute f of 0? Yeah, f of 0 is what? 0. It's defined here on the second piece. So yeah, it's defined as 0. The second item, checking continuity at a point. The second item is then, does the limit as x approaches that value on the actual function exist? So for us, that's the limit as x approaches 0. I'll say this is a here. The limit as x approaches 0 on our function h of x. Does that exist? Yeah, how do we know? Oh, I'm running out of space. Well, that's the limit as x approaches 0 on x sine of 1 over x. So as x approaches 0, we have a 0 times, what's the sine of 1 over 0 in the sense of a limit? If the numerator stays fixed and the denominator gets smaller and smaller, approaching 0, what does the argument turn into? What's 1 over a smaller and smaller number? A what? Infinity. Yeah, it's a larger and larger number. So we already talked about what is the sign at infinity. Yeah, we have to use an inequality because the sign at infinity doesn't exist, remember? It's between 1 and negative 1.
Doesn't it, in the piecewise function though, it says, like, we have to use that formula if x is not 0.
Right.
So why are we using that formula?
Okay, so x is not 0 for that piece. Why are we using this piece, computing the limit as x approaches 0?
Because it's approaching 0, it isn't 0.
Right. Remember, the limits don't care about what's happening there at x equals to 0. It just says as x gets closer and closer to 0, what does the function get closer and closer to? Yeah, good question though. That's very valid. Just a good reminder when we actually compute a limit what it actually means though. As x gets closer and closer to something, what do the function values get closer and closer to? That's all a limit is. Even though we do write equals. All right, well, I'm just going to write the answer here, and you can verify it for yourself. The Squeeze Theorem. So what we have is item 1 is defined, item 2 is defined, and then all item 3 says compare 1 and 2. Are 1 and 2 equal to each other? And if they are, then all 3 conditions are met. I'll just shorthand this. Does number 1 equal to number 2? Yes. The function's defined at 0 as a value of 0, and the limit has a value of 0. So since all 3 of these are true, we would say that h of x is continuous at x equals to 0. But again, all 3 conditions have to be met. Okay, does anyone have any questions about that? So in order to use the definition of continuity, like I said, we're going to use the checklist. Anytime you're asked, is this thing continuous here, then make sure that you're justifying all 3 of these. So here we'll use the figure to determine where the function is not continuous, and then we'll use the checklist to justify our answers. So we can just list them off. There's a few of them, but for each one we list, we need to justify why that's true. Okay. So where is one value this function is not continuous?
X equals 1.
Okay. At x equals to 1? And why is it not continuous at x equals 1?
Open circle.
Yeah, there's an open circle.
F of A is not defined.
Right.
The first clause.
So we want to make sure that we're explicitly tying it back to the checklist. Don't just say, it's correct, there is an open circle there, but in the sense of continuity, what does that mean? That means the function isn't defined at that value.
The limit value isn't equal to the function value.
For which one?
Oh, wait, I was talking about my that's for 2.
Okay, all right, yeah.
I skipped it.
So this is why the function is not continuous at x equals to 1. Okay, where else?
X equals 2.
At x equals to 2. Why is the function not continuous when x is 2? Right, right. So we see that the function does exist at 2, and that value is 3, We know the limit exists as 1, but the limit value is not the same as the function value. This is F. Make sure, yeah, this is F. So the item 3. Yeah. Where else?
X equals 3.
X equals to 3. Why is the function not continuous at x equals to 3?
The limit doesn't exist.
Okay. So is f of 3 defined?
Yes.
Okay. So don't just say there's a jump or a break in the graph. It's true that there's a break in the graph, but that's not technical. That's just like a visual aspect. So which item corresponds to x equal 3?
Number 2.
Number 2, yeah, the limit does not exist. So the limit as x approaches 3 does not exist. So someone on this side over here, tell me why that limit doesn't exist.
It's only on one side of the limit.
Meaning,
You can approach it from the right, but you can't approach it from the left, so it doesn't exist.
okay, yeah, that's pretty close. We can approach 3 from the right. Can we approach 3 from the left?
Oh, yeah.
Can, but the
Yeah, but
values are not.
but they're yeah, right, but they're not equal. So the limit from the right does not equal the limit from the left. Anywhere else? At x equals to 5. Why is it not continuous at x equals to 5? There's a vertical asymptote, okay? So what does that mean about our checklist? Number 1, yeah, the function is not defined at x equals to 5. There's a vertical asymptote there. Yeah.
On my math lab, it says it's breaking rule number 2 too, but there is a limit there, right?
Right. Yeah. So what about number 2? What is the limit as x approaches 5?
This is infinity, so it would. All right, that makes sense.
Yeah. I mean, and technically we should be specific. 5 from the left, and the limit as x approaches 5 from the right and from the left. Both of those are infinite. But does that mean the limit exists? No, limits are finite numbers. So even though we can quantify that as x gets closer to 5, the function keeps growing, that doesn't mean there's a limit there. It just describes a vertical asymptote. So I guess, you know, if my math lab wants you to describe both of these, then you should do that. But really, one is enough, right? The function not existing there, doesn't matter if the limit exists or not. The fact of the matter is that they can't equal each other, so it's still not going to be continuous. Okay. Any questions about that? Yeah.
On the graph, you're not able to determine continuity at x equals 0 and x equals 7 given this graph, correct?
Well, yeah. So that's a good question, and that's kind of where we're moving towards when we talk about continuity over an interval. So if we ask the question, is the function continuous at x equals to 0 and x equals to 7? Right now what we would say is probably I don't know, right? Because the definition of continuity at a point is stated in terms of this two-sided limit. So what would the modification be there if we did want to know, is the function continuous from the left of 0 and from the right of 7? Well,
We need to see the graph.
We need to see first.
well, we don't necessarily need to know the equation,
No.
We just need to know what is on the graph there.
meaning that we just compute what?
X
The-
-1 or something to the left of that value.
Which is what kind of limit?
Left-hand limit for 0 and right-hand limit
X,
for 7.
Yeah.
as x approaches negative numeric value.
Right.
whatever.
Or specifically, we're just looking at a one-sided limit, right? Only one-sided limits make sense here. And here. But just visually, we could say that if we modified that limit to just be a one-sided limit, it would be continuous. The function exists. The limit as we approach x 0 from the right is equal to 3. So the limit and the function value are the same. But that kind of idea kind of extends to, over what interval is this function continuous on, rather than just at a particular point, is it continuous? Okay, yeah, good question. Any other questions before we move on? So a couple of examples. Given f of x, is the function continuous at a? So example 1 is 3x squared minus 2 over x minus 1, continuous at 1?
Would be no straight out the gate, wouldn't it?
Yeah, no, and how do you know that?
Because it fails the first rule.
Yeah. Item number 1, f of 1 is not defined. In other words, what we're saying is that an x value of 1 is not in the domain. So hopefully that's fairly intuitive. How can you be continuous at something that's not even in the function? It doesn't make any sense. And that's what we'll see, like for most of these functions you've seen up to this point. The exception are the piecewise defined functions. But like all of your algebraic functions, your trig functions, your inverse trig functions, all of those functions are defined on their domains. So, it's kind of, with the exception of piecewise functions, like I said, the notion of continuity and the notion of the function's domain are very, very similar, if not exactly the same. So how about example 2? Is that function continuous at 3 and 4, x equal to 3 and 4? No?
3 isn't 3.
Not that I
We need 3 over 0.
Yeah.
Item is 2x.
So we could just plug them in to see what happens, or we could factor the denominator and see that we have a similar situation as in example number 1.
So would it be safe to say if you're going through these rules, two is entirely dependent on the outcome of rule 1,
Yeah.
essentially,
Yep.
right? Because if it doesn't exist, then there's no limit to evaluate.
Yeah.
So rule 2 isn't even something to consider.
Well, technically, just because the function doesn't exist somewhere doesn't mean that there's not a limit at that value, right? You know, and a perfect example of that is a function that has a hole. That function doesn't exist at a, but the limit exists as x approaches a.
So if that's the case, when we are saying it doesn't, oh, I guess that really doesn't matter, right? Because even if it's if it's no to rule 1 and it's yes to rule 2, it still fails rule 3.
Exactly.
So it's irrelevant.
Right.
If it fails any of the rules, it fails continuity, the continuity test.
Gotcha. Okay.
And of course, by implication, when we say it's not continuous here, 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 and here, or it's not continuous over this interval, what we're getting through implication is that we know where it is continuous, right? So if it's not continuous at 3 and 4, is there anywhere else it wouldn't be continuous? No, the only goofy things that happen are at 3 and 4, right? Specifically with this type of this function here, what happens at x equals to 3 and x equals to 4?
Asymptotes.
Yeah, we know they're asymptotes because those factors don't cancel away. Is that straight? Sure. Good enough. So, you know, whatever the function's doing, it's doing something like this or like this. It might be doing something weird in the middle or something like this up here, down here, whatever the case may be. We know there's not anything weird happening elsewhere. So we're saying that I know where it's not continuous tells me I know where it is continuous as well. So I don't know, look at it visually, not at 3, not at 4, but everything else. So it's continuous from negative infinity to 3 to 4, and 4 to infinity. We have to talk a little bit more about this because it's not quite complete. And in the sense of these rational functions where we can like quickly remember what the graphs look like, hopefully, we definitely know 3 and 4 aren't included. But there are functions where we have to test, are those values included from the left or from the right? Okay, so there's a lot of theorems in this section. We're not going to really focus on them a whole lot. We will talk about like what they mean. But these theorems deal with continuity of various types of functions and combinations of functions. But we just remember that functions will be continuous on their domain. And really the only exception, like we said, piecewise function. Piecewise functions may or may not be continuous on their domain. So like here's a piecewise function whose domain is all real numbers, but it isn't continuous at A. But for like algebraic functions, trig functions, inverse trig functions, all of those, their domains are directly related to continuity. All right. So continuity rules. We're going to look at f and g are two continuous functions at a point, x equals to a. Then the theorem says then the following combination of functions are also continuous at that value, x equals to a. So we have f plus g is continuous, f minus g is still continuous, a constant times a function f, or this could be a constant times function g. The two functions multiplied by each other, and the function raised to a positive whole number power. So So basically, this theorem says that if you have two continuous functions at a point, then combining the functions in that way, via those operations, doesn't affect continuity. These operations.
What about E?
What about E? What do you mean?
Why did you circle that? Literally all of them but E.
Oh, because E just has that caveat. So notice that if I have two continuous functions, let's say they're continuous everywhere for all numbers, but then I divide them, then the same rule still applies. If you divide by 0, then you have a problem. So that's the caveat here in E. If I divide two continuous functions, they're still continuous provided that I'm not dividing by 0, provided that the denominator at that value is not 0. So dividing can affect continuity, right? So if I had a function x plus 1 and x plus 2, they're both continuous everywhere because they're just linear functions. But when I divide them, now this function isn't continuous at -2. So it does affect continuity when you start dividing, depending on the functions. But again, I hope that's just straightforward from, all of the algebra and pre-calc where that's still true. Polynomial and rational functions. So a polynomial is just continuous everywhere. A rational function, as we've seen, it's continuous everywhere. Its denominator is not 0. And we've seen examples where we had like polynomials where the denominator does factor out, like x plus 1 over x plus 1 times x minus 1. That rational function we know simplifies to 1 over x minus 1. So would we just say that this function isn't continuous at x equals to 1, where it has a vertical asymptote?
X equals -1 beta.
Yeah, because the thing that canceled out, remember there's a hole there. So we're saying that it's continuous everywhere its denominator is not 0 before you reduce. Continuity of composite functions, composition. So g is continuous at A, then f has to be continuous at g of A. That means the composition is continuous. And I think that's a little, we could illustrate it kind of simply if we say that composition, we're putting g inside of f. So like if f were the square root of x and g were, I don't know, linear function, let's just say g is x plus 1. Then when we look at its composite, f of g of x, square root of x plus 1, same rules still apply. This function is only continuous for when we're not taking the square root of negative numbers. So even though the function g is continuous everywhere, when we put it inside of f, then we have restrictions on continuity. And it really just depends. But this function is just saying that if g is continuous at a value, f has to be continuous at that output, right? So if I plugged in, if I plugged in -2 to g, g is continuous at -2, but g of -2 outputs -1, and f isn't continuous at -1. So that's kind of what that's saying. F has to be continuous at the output of g in order for us to compose those two functions and still have continuity.
Can you have continuity if you have an equation or an expression of any kind with I in it, the actual letter, to represent that negative with roots?
You would have continuity in the sense of the complex plane, but not in the real number sense. You wouldn't have continuity.
Okay.
Yeah. So yeah, if anybody goes on in math, if you study complex numbers, you can actually do calculus with complex numbers. So the complex numbers are what they call a field. We can do calculus, differential equations, algebra, trigonometry with all of that stuff. But it's totally removed from or a separate thing than the real number system.
Okay, so in our
Yeah.
case, our theorems are just referring to real numbers.
Yeah, always under the assumption that we're dealing with real numbers. And if you see math classes that are called elementary something, then that's the assumption, is that you're talking about real numbers. So like this is elementary calculus. If you go on to like complex analysis, when you start seeing complex, that's when you look at imaginary numbers. And so this is another theorem dealing with the limits of composite functions. And basically what it's showing is, can I pass the limit through one of the compositions? So like if I had to compute a limit as x approaches a on the square root of x plus 1, when is it okay for me to do this? So I think, the theorems are pretty in-depth and involved, but I think in practice, when it actually shows up for you to determine continuity or to compute a limit, that just from an algebraic or pre-calculus standpoint, you recognize what I can do and what I can't do. So these theorems, along with the notion of continuity, are the reason why a lot of functions we can just directly plug the limit into and evaluate it. So the continuity, we'll say, gives us the y behind direct substitution. For example, just that kind of direct substitution.
So those, is that continuity, do those rules generally follow the same rules from like 2.3 or 2.4?
2.3 was limit laws, like what we could actually do with the operation of a limit.
Mm-hmm. I mean, I guess more so just the reconstruction of the limit, expressing it one way versus another.
Yeah.
Does that tie with the continuity stuff?
Yeah, it ties in, because remember when we looked at the limit of like f divided by g, we said that limit is the limit on the top divided by the limit on the bottom, provided that the limit exists.
Right.
So yeah, I mean they're closely related, but limits in general are quite a different thing than continuity. So we have to look at them as kind of separate, even though the rules look very similar. So the continuity is defined in terms of a limit, but limits in general behave in certain ways. And based on how they behave will tell us if something's continuous or not. I don't know if that's helpful. Okay, so that's continuity at a single point. Then we'll kind of broaden our horizon and say, given a particular function on what intervals is it continuous? So the statement is it's continuous on an interval if it's continuous at every single point in that interval. And really what we see here with these two pictures or these two graphs is that makes sense except possibly at the endpoints, right? So I'm continuous at all of these points in that interval, and I mean that totally makes sense for all of these points. Well, what about our endpoints? So notice how this is saying that this function is continuous from A to B, where we include A but we exclude B. That should be evident from the graph itself. But in practice, determining continuity from this direction as I get closer and closer to B, or from this direction as I get closer and closer to A, does involve one-sided limits, as we sort of noticed earlier. And then this kind of jargon here that's associated with this, we're going to say that this is continuous on this interval from A to B, including A, or we could say that it's right continuous at A. So meaning as we approach A from the right, that we're basically including that as part of the interval. So the function is defined at A. As we approach A from the right, the limit is also the function value, so then we can say that it's right continuous. We can't say anything about it being completely continuous because continuity again was defined in terms of a two-sided limit. So it's just a matter of context. Here the context of a two-sided limit doesn't make sense, so we sort of throw that out and look at a one-sided limit, but then we have to be more specific in how we're describing continuity. It's continuous from the left, it's continuous from the right. That's really the only modifications we make.
So you're saying it's continuous at a specific domain, but the expression as a whole is not continuous?
Yeah, well, I mean, we would say...
Whatever that expression may be, you know, whatever f of x would equal, that as a whole is not continuous, but it is continuous at certain points.
Yeah, it's continuous at every point in this interval.
Okay.
I mean, you know, really where you start is you say that it's continuous on this interval here, and then based on the context of the function, if I compute the limit as I approach A from the right, and it's equal to the function value, then I would say that it's continuous here, like that. If I compute the limit as we approach B from the left, and it's equal to the function value, then I could say it's continuous on this interval. So basically the one-sided limits here on intervals are going to tell us, do we have a parenthesis or a bracket around that number? Is that thing included or is it excluded? And again, I think it's really straightforward when we look at a graph, but when you're just given a function and you don't know how to graph it, it's much easier to compute a one-sided limit to determine if that's actually included or not. Similarly here, as we approach B from the left, that's the limit is defined as the function value, so it's left continuous at x equals to b. And that jargon is defined here with continuity at the endpoints. A function is continuous from the left, so you could say either or, continuous from the left or left continuous, whatever you want to use. So a function's continuous from the left at A if the limit as x approaches A from the left is equal to the function value at A. So that's the definition of continuity right there, modified with a one-sided limit.
Is that bottom one, the limit as x approaches A from the right?
Yeah.
A positive?
Yes.
Okay.
And again, you know, like, why would we do this? Just think about piecewise functions like those two graphs above. It only makes sense to approach from one direction. So that's how we're going to test continuity at endpoints. And continuity at an interval just means that it's continuous at all points in that interval. And then what we see with a few of these examples is from the right or the left at the endpoints. So usually it's those endpoints that are questionable, where we have to compute the limits, the one-sided limits. All right, and so an example of where those one-sided limits are appropriate is something like a piecewise function. And naturally, it's kind of a moot point if both of the pieces are connected, right? So like if you have a connected piecewise graph, and it's just like it's continuous everywhere. The point comes in and fills the open circle in. So in reality, it is a lot easier to like look at it through an algebraic lens to determine. But let's just say we forgot how, or I don't know how to graph this, nor do I want to graph this. So how can we determine intervals of continuity? So this function is defined, this piece is defined at 0 and everything smaller than 0. And our bottom piece is for everything larger than 0. So first of all, what is the domain of the function? Yeah, the domain of this function is all real numbers. But that doesn't necessarily mean that it's continuous on all real numbers. And so really, where's the issue? At what x value do we have an issue?
0.
At 0, right? Because you see something funky might happen at 0, because the one piece is defined there, the other piece is not. So the first thing that we're going to look at is f of 0. Is f of 0 defined? And if so, what is it? F of 0 is defined as 0 squared plus 1, which is 1. And the second thing we have to look at, so we said that this function is, first of all, the domain was all real numbers, but then we said we could possibly have an issue at 0 and only at 0, right? So we're kind of backing up and saying if that's the only point where we have an issue, let's look at continuity at that point, because if we know where it's not continuous, by implication we know where it is continuous. So that's kind of our approach. What's the limit as x approaches 0 on this function? Well, that's where we have to do what?
You have to look at each side of the
Yeah,
limit.
one-sided limits. When we see that from each piece's domain visually. So what's the limit as x approaches 0 from the right on f of x? 5, what do y'all think?
5.
Okay. If we approach 0 from the right, we're larger than 0. So we're using the piece 3x plus 5, which is equal to 5. So in this process of trying to identify are we continuous at that point, notice where we're at right now. We said the function is equal to 1 at x equal to 0, and now we know the one-sided limit from the right is equal to 5. So we can stop there and already draw a conclusion. So we're approaching 0 from the right. Then let's ask the question: is f of x right continuous? Well, if we just said, is the function continuous, we compute a function value and a limit, then what do we have to do with those two things?
They'd be equal, right?
Right, the third item on the checklist says, are those two things equal? So we just modified that to a one-sided limit. Is the one-sided limit equal to the function value? No. This one's 5 and the function value is 1. So if we ask, is it right continuous, the answer is no. The limit as x approaches 0 from the right does not equal to the function value there. Does not equal to the function value. So we know the function isn't continuous from the right at an x value of 0. Then by implication, what is that telling us about the interval of continuity? If it's not right continuous at 0, I'm approaching 0, here's 0. I'm approaching 0 this way, but it's not right continuous at 0. So what does that mean?
It's left continuous because we've already proven that 0 is defined.
Yeah, so we have this parenthesis around 0 as we come from the right. Does that make sense? It's not right continuous at 0, so we wouldn't include that. So what we're saying, the implication here is, it's not right continuous at 0, but it is continuous on the interval 0 to infinity. So in other words, I can approach 0 from the right, but right when I get up to that value of 0, the limit isn't the function value. So we can't include that 0 as part of the interval of continuity because the function isn't continuous there. So if we said it is right continuous, the only change we would make if it was continuous from the right, in other words, if this limit as we approach 0 from the right came out to be 1, the only change we would make is this right here. If it is continuous from the right, you have a bracket. If it's not continuous from the right or the left, then you have a parenthesis. That's really what that is equating to. So it's not right continuous. And it's kind of opposite, right? We're talking about right continuity, but we're putting the bracket on the left because we're approaching from this direction. We're approaching 0 from the right. So the idea of what we're looking at is easily summarized by looking at the domain of each piece, but as far as like the limit is concerned, we're using the limit to tell us which one of these gets closed off and which one of these we include, if any. So it's the same as what you did in algebra and pre-calc, but again, we're just putting the context of a limit to it, which makes it a little bit more involved. So we'll pick up here on, Tuesday? Yeah, Tuesday. See ya.